mention that.
Okay.
Yeah, his work was suppressed by the Soviet Union back in the 60s or so. He had published a book. It was supposed to be 500 pages long, and they cut out 200 pages. This guy was flying on bee honeycombs across to the landscape. It's totally amazing. I'm going to speak on this at the next at the meeting in New Mexico this summer.
He also he mentioned in his book also about those honeycombs that he first noticed it when it had physiological effects on him.
Right.
Right, when he was laying on the ground, so that should also be detectable too.
Yeah, he was saying it can be used to alleviate headaches. He made a special chair you sit in with the honeycombs over your head. And within an hour, you get rid of your headache. There's a beekeeper that has his shop below me, and we're planning to build one of those chairs. But you'll find the Grebennikov stuff very interesting. Subquantum kinetics explains the effect. Nobody has yet to this date understood what causes the effect. But in subquantum kinetics, it can be explained, and I haven't written it down, but I think it will lead to patentable stuff. If you can imagine the honeycomb of a bee is like a cylinder that's open at one end. And when you charge that up, it's going to, if you think electrons are going to align that cone, electrons put out exons and geons. And so the cone, in effect, is going to direct them out the end, sort of like a laser. And they just keep going. And he was able to get that to produce gravitational repulsion and actually levitate himself. He's able to levitate his whole body.
Mm-hmm. It would be an EED, Etheron emitting device.
Yeah.
Yeah.
And I'm thinking it could also be used as a weapon. You can use it in place of a gun. You give the guy sort of like you socked him in the face or the shoulder, just by pushing a button. I mean, for police, I mean, that would be a better alternative to guns.
Would that be similar to the Podlikhanov device?
Yeah, it would do the same thing that Podlikhanov was doing, but a lot less expensive.
Mm-hmm.
The Russians have his thing out in classified area in Moscow, and they won't let him do any more research on it. They consider it a weapon.
Yeah.
So I was going to ask, David had done a bit of writing about points of concern.
Yeah, I've been thinking on the subject, and I see that some questions need to be answered. And I have made comparison to like already known things in like diffusion systems, and also regarding vacuum, because vacuum and ether are very much together. So I'm now going to share my screen here and see how it works. Can you see this?
Yeah.
So you see the flow here. I can scroll up a little. It doesn't, let me see if I can get whole screen here. No, it doesn't allow that. Okay, I have to scroll a little. I mean, in diffusion systems, if vacuum is like a reaction diffusion system, and there is motion in relation to this, then it's possible to imagine like three common types. Stationary, there is no problem, right? And there is like a suitable theory for how it diffuses. But if there is a motion in relation to the fluid or the medium where the particle is or the matter is, then it becomes different in different directions.
Compressed
get
in the
physical.
upwind and extended in the downwind side, huh?
Yeah, in this picture it is like that. Of course, it can be more complex in various situations.
Yeah, I visualized it that way too.
Yeah,
It's interesting, CERN, they haven't found any evidence for length contraction. And
No.
they've gone up to a point where they should have seen a tenfold pancaking, and they haven't seen anything.
yeah, yeah. It's actually I'm not touching on relativity versus non-relativity because I don't have to in this in
Yeah.
these two pictures that these two slides that I'm showing.
Hmm.
So we can avoid the topic of how applicable eventually relativity is or not. But if it's fluid, then usually Navier-Stokes is used. And this is when the fluid is coarse model. The fluid is always consisting of particles. And when we speak about fluid speed, they have just made arithmetic mean of fluid particle speeds. And
Right.
since the etherons are like more complex, more constituents, maybe the third model here of particle systems has to be used.
The difference is that on top of a standard computational fluid dynamic system, you have to add reaction and diffusion, two more
Yes.
computation
On top of
elements.
that, yeah. It becomes even more complex than this. And I think at least that this third model has to be considered. And then there are various, I just mentioned two that I know of here. This is just theories for the transport of these particles. And in one case, they use statistical averages and constitute different parts, different suits of speed ranges for the particles. And as you can see in this model, net speed is 0 here, so it's a stationary fluid. That is opposed by these two, and this goes to right and that to left. So in like stationary air, you have actually a mean root square speed of 300 meters per second, and you do get effects based on that. So this course model,
Could you explain that again about the speed?
yeah, like Navier-Stokes, it speaks about an explicit point defined speed, and that's as is an arithmetic mean of fluid particle speeds, because all continuous media consists of particles.
But you were saying about 300. Where did you get that?
That's just common air at 20 degrees Celsius. So we have a lot of speed at particle level in air, although it might be stationary and non-fluid. So effects on a small scale can be big, although the fluid speed is 0. And I guess that subquantum kinetics need this third type. And I'm also going to mention additional arguments why the complexity can't be less. And you see that on the last line here. Neither model is Lorentz-Galileo invariant. And that means that Newton's first law does not apply. Because you do get effects if you move this.
What is not Galilean invariant?
Yeah, Lorentz and Galileo invariant are just things, physical systems that are invariant under transformations where there is a speed. So if you have a speed like between these, for case 1 and 2, you do see that you get an effect just because of the speed of the material in the fluid. If we have vacuum, we think that there is no such effect. But I'm going to tell further on that these effects do also exist in the traditional vacuum models. So Lorentz-Galileo invariance just means that you do not get any physical changes in physics if you move these with constant velocity, which is also what the Newton first law says. So we do have problems that are going on a very deep level in physics. And if we don't have this kind of invariance, we get effects that we do not see and which is like apparently not present. And maybe I can show you this if you now go over to my next slide here about vacuum ether, I don't need to differentiate between these two concepts for what I'm going to mention. And that is the vacuum problems. Maybe you have heard of the cosmological constant problem, where the energy content of vacuum is super high between two different ways of describing them. It's actually the biggest discrepancy ever in physics.
Hmm.
And yeah, the traditional density distribution, I think it's like was made in the 50s or 60s. They said that it has to be these criteria, and they used some theory to describe it. So they got this cubic dependency. So the distribution function of the density of the electromagnetic radiation in vacuum increases cubically. So if you have like 10 hertz and want to know how, if you have a certain intensity, say at 10 hertz, and then you go to 20 hertz, yeah, then it's 8 times more intense at that frequency. And if you are up at gigahertz, it's extremely much more, and it goes on forever.
So what type of frequency are we talking about here? We're talking about electromagnetic. What type of frequency?
Yes, we are talking about electromagnetic frequency, radio waves.
So
or
like
light.
the wavelength, as the wavelength goes down, the volume goes up by the cube. Huh?
As the frequency goes up, the wavelength goes down, yeah. So imagine like a graph where energy content, the intensity at that frequency increases. And there has been different ways of like explaining why it's not infinite, that the Planck frequency would be an upper limit. And another way of reasoning is that the limit would be where matter is no longer interacting with that frequency.
Yeah.
And very high, beyond gamma radiation, even higher, matter does not react, so it doesn't matter.
Right. But nonetheless, this is a singularity within the model. You know, if you throw out and say, okay, Planck frequency is the singular point where it's basically stopping, and so the model stops working basically at a certain point. And paradoxes and singularities and you know, non-constant features are common in pretty much every computational system. That's not something surprising, but you want to minimize it, and that's why, you know, one of the benefits of the subquantum kinetics is that you're treating the ether as particles. Not only do you have the continuity of the particles and their interaction in creating the frequency, but you also have the representation of particles both at the cosmological level, the macro-micro level, the atom particle level, but also at the subparticle level. So you're using the same particle type model across all of the different domains, which is an important computational feature.
Yeah. But since we know that inertial systems are physically identical, I think that has to be the basis when developing models here for ether or vacuum, to ensure that this feature is not disturbed.
Right. You don't want to have. I think we're saying the same thing. We don't really want to have that Planck frequency as sort of a limiting factor.
No, and it's very reasonable just to have interaction limits. Then you get even lower, I think. And actually, if you have the interaction level will matter, you might work around this non-Lorentz invariance, because maybe you can, and also you can hypothesize regarding a vacuum with superluminal content. Then you might also find a balance, but we haven't investigated the question in that way.
So thinking of, you know, if we're using this representation of the vacuum of the ether as having particles, like subquantum kinetics does, if we have that representation, and you think of, jet engines throwing wind and traveling using speeds to go faster than sound using air, well, you can think of the same type of contraption created in the ether. That's basically, taking the ether and sending it behind. So you can create a jet engine or an ether engine that's faster than the speed of light. I mean, that's nothing that would be unusual if you're using, an etheric model that has particles, subparticles that have the same type of composition that air has. At the particle level, you're talking about everything from particle perspective and particle interactions and throwing the particles, via some type of engine.
Yeah, it is possible to model vacuum as some kind of superfluid where you don't have viscosity, so you can move it with a constant velocity, but you do notice it if you change velocity.
But in subquantum kinetics, to get gravitational repulsion, you need gravity waves. Just the ether flow is not going to cause any force. Right?
Yeah, I have nothing to say there because I haven't investigated or thought that far. But do you think that question or could help in?
So there's an important thing is that every particle, which is the structure, you do have to get those flowing, so that it's definitely intertwined, the electromagnetic and the gravitational, because all the structures that you're trying to move are composed of those things as a interconnected unit, and you do have to get those to move. But if you can grab the ether and send it back while maintaining that structure, yes, I talked about numerous times, that there's been concepts of discrete mathematics, continuous mathematics, but something that's emerging is this gradation type mathematics, where you're making jumps, but it's within a continuous medium, but you can only make those jumps. So it's I'm agreeing with what you said in that there's a structure there, and that's sort of like a gradation, all the particles, but you're still trying to get the ether to move back, but you have this restriction, is that you don't have a plain air type environment. You've got this structure that you're trying to, get the ether to flow around, so yes, there is all of this interconnection and additional complication, because you're working with structure and you're trying to get the structures to move, even though there's a general ether there. I don't know if.
Well, it's the gradient of the ether that causes the structure to move.
Okay.
It causes distortion of the particle's space structure, and the particle tries to reestablish its symmetry, and in so doing, it accelerates, creates itself in a new velocity frame, and keeps doing that as it accelerates. Also, we may have evidence of being able to slow time down with just with an ether flow. Sort of like as if you're traveling very fast at relativistic speeds, so you get an ether wind causing your time dilation. At least that's the standard claim.
But can we really talk about ether winds? If is ether then like a fluid with an explicit speed, or is it more like a particle system where there is a lot of speeds in all directions at the same time?
Well, if you're traveling at, let's say, 70% the speed of light, you're gonna, the ether is gonna be going by you. I mean, I don't understand.
But can we see in a cosmos somewhere where we have like very high velocities, can we see any strange effects when particle moves almost like the speed you mentioned?
Well, there's those experiments on the on.
Would the blue shift be an example?
Well, this is going way away from what I was trying to say. What I was trying to say is we think we have controlled time in the laboratory, and we're doing the experiments now.
Is it controlling time, or is it controlling
The
the
flow of time.
interactions that are happening?
We're able to slow down time, we think.
Is it slowing time, or is it the ether slowing down how things are happening?
Ether.
The ether is slowing how things are happening. So it's sort of like getting
We have a
water in the way
machine.
when you're swimming. You slow things down.
We have a machine that creates an ether wind. Okay, we haven't measured it with an interferometer yet. At least when we did the experiment, the original experiment, we didn't have an interferometer, but we did observe a time dilation. And we're going to be repeating the experiment.
But from an ether model, do you want to consider that slowing time, or do you want to consider that like water? Water slows people's movements. So you have an ether motion. It's going to slow down.
The reason I'm bringing it up, when the ether's flowing relative to the particle, I was theorizing that the interactions, the reactions are going to slow down for that particle because it depends on encounters between etherons. So if the etherons are going by your frame of reference very fast, there'd be fewer, well, it would be a slower rate of interaction. So that was the idea I had of what might cause time dilation.
My own preference is to get completely away from the relativistic model because it adds all these complications you don't need. And just say one time dimension and you know, 3 physical dimensions. That's all you need from a computational perspective. That simplifies everything. That's a
well, okay. I should correct what I said. We're not talking about the flow of time in the big sense of capital T, but clock time on Earth, so to speak.
How fast the clock moves, right? I mean, basically, the ether flow is slowing the clock itself. Just, you know, it's slowing everything in the space that it's around. It's basically slowing the people, slowing the clock, slowing everything there.
That's exposed to that ether wind.
Yeah. And that way you can maintain that simplified model of constant time, you know, and 3 physical dimensions. And that's all you need to do your representation, which is a huge advantage.
The constant time is really the ether flux below everything at the subquantum level.
And from my understanding, that as far as relativity concerns, that the subquantum kinetics has some relativistic effects, the good relativistic effects, and the other relativistic effects, or say special, were not included. Is that correct? So the subquantum kinetics has some relativistic effects, but not.
I would say that all of those effects emerge.
Yeah.
All those behaviors emerge from the very simplified model. So I'm trying to say, let's use that simplified model and see all these behaviors that we do see, including relativistic behaviors. Those are things that emerge, but we don't have to, you know, attach a warping of time or a warping of space to anything. We can just say we've got particles and interactions of particles, and that's it. You know, computational fluid dynamics plus reaction diffusion. And we're done. We don't have to add all of these additional features in order for the system to be effective.
I tried to find the paper that you cited in the SQK book on rotational waves under the topic of rotational waves. I wasn't able to get it through the UCL account. That was one of the ones I wasn't able to get. I think it's reference 22 in, I think, either chapter 5 or chapter 6.
But what I hear from you is that, like, the case 2 in my picture is what you're aiming at. like a traditional common fluid with an explicit speed. Is that, you think, suitable here? Is that enough as a model? Because you do not get motional invariance then, which is so very much established that we do have.
So can you explain that more? Emotional invariance?
Motional invariance, yeah. If you have a background or a vacuum or an ether where you have effects on matter, if you move relative to it, then we are very much away from what we have experienced in physics this far, that we do not have any kind of effects if we move systems with constant speed compared to each other. There is no physical effect in that.
Right.
So if you can, as far as I see, you do get this kind of effects if you have a vacuum of case 2, traditional simple fluid type of vacuum or ether. So if you just model that vacuum as a Navier-Stokes stuff kind of thing, you do get a lot of motional effects, effects that doesn't occur with the kind of vacuum or void that we know since hundreds of years.
So it's a major problem for
Yeah, that
using.
seems like a major problem, and the same problem is present with quantum electrodynamical vacuum as well. But since there is no effect or no practical use of it, it doesn't cause a major concern today in physics. But it is definitely recognized as a problem.
Okay, but in physics, physicists can get away with it with their theories because they're convinced their theories are already correct.
Yeah,
Whereas we would have to prove
postulate.
in our case.
Yeah, they just postulate a certain characteristic, but it's not there. And they do say that quantum mechanics is not compatible with relativity. So it's well known, but or maybe it's not used in subquantum kinetics either. Maybe this mission doesn't give any big problems. Depends on what kind of application you're looking for.
Okay, so if the spin is due to vortical motion, due to hydrodynamic fluid motion, how would that change at a different velocity?
Yeah, I think you get more opportunity if you use a more complex model like particle systems, and but it becomes much more complex. But maybe that can be a way to get through here.
I mean, are you really sure it would be a problem? I mean, maybe we should try to simulate this or something. I don't know.
Well, if you have make the effort and do the model, it would be interesting to see. But maybe it won't be a problem, depending on what you're going to use it for.
So my view is that you've got this more complex system, the particles that I'll just use CFD, the computation fluid dynamics, reaction diffusion, CFD-RD. That's sort of like the complex model, but then you can have all of these simpler computational models. You can actually simplify the CFD-RD too, depending upon what type of computational system you use. So you have all of those, but then at the higher level, when you're trying to represent something like, let's say an energy equation or a, inertial equation, what have you, you're trying to summarize the behavior of all these small behaviors that are happening. And so, if you're talking about, let's say, and I talked about this last week, where you've got the spin, okay, so you've got a particle, and we know the particles have spin. So whenever we have all of these reaction diffusions, we know that at some point we're going to have, spin within that particle. Now, the equations that Matt Pulver wrote, he wasn't looking at the motions of the etherons within that created particle. He was looking at the quantities, how much, exons, yons, dions were at each location. He wasn't looking at trying to say, well, what's the trend for the movement of these exons, yons, and dions? Is there a spin created or not? That wasn't part of the information pulled out of the equations that he was running. We might be able to do that to see if there is some type of spin created when we're seeing all those reactions. Plus, we also have light. Okay, so with light, and I know in the book, the light is sort of like the same type of reactions that are happening, you know, in a waveform as opposed to being wrapped together in a particle. And so those light waves are happening, and you have all of these reactions that are happening in space. But then they, let's say the double slit experiment, they hit, you know, the particles in the double split, and then they break apart and they go in different directions. Now, because we're looking at a gradation type behavior with subquantum kinetics, as opposed to discrete behaviors, we can see that these waves interacting with the particles on the wall would send things in specific gradation directions. So you would realize the double slit experiment, and you don't have to have particle versus waves. You basically just have to have particles interacting, and there's associated, you know, spin. So I'm trying to say that even a simple example like the double split experiment, you don't have to go to the more complex, you know, vacuum behaviors. Just some of the more basic examples, we can see that same type of behavior where you're seeing spins react with each other.
Are there software, open source software for computational fluid dynamics with reaction diffusion?
I have looked, you know, that there are some. You have to get into it. I've seen that people have added packages to one of the open source CFD systems, but it looked like it was, you know, a lot of hand done stuff. So you really have to replicate what they've done and try and capture that. I've also seen, you know, going through all the different computational systems, I've seen a lot of different reaction diffusion systems, some of them that would run faster than CFDs. You know, so the whole idea is try and use the simpler model to start out just to get some idea of what's happening, then go to the computationally more expensive ones as you start understanding how things are happening more. So you have to get into a lot of different, and a lot of these are out there on the web for you to pull in the code and start fiddling around with, but you really have to get into it. You have to spend some time.
So that would be a bit like merging computational fluid dynamics with, say, Matt Pulver's code on ETD stepper. So like merging the two, or?
Well, he was doing differential equations. He wasn't really doing CFD stuff at all. CFD is going to represent more, you know, at the subcomponent level, and the behaviors at the subcomponent levels. He was just measuring, you know, at this point on a 2D surface, how much exons, how much yons, how many geons were, and he did a nice chart on that. Whereas, you know, CFD is you're working with a three-dimensional space, and you can pull a lot of different information depending on the different features of it.
But do we need it in 3 dimensions? Can we just look at, say, the 1-dimensional or 2-dimensional for simplicity, just to start with? Hello, have we may have timed out. Hold on a minute. Can you hear me? Okay.